Hi there, welcome back. Today we're doing 5.2.6 for CPM's IM2. Today's topic is imaginary numbers. What are they? Our learning goals are twofold. One, that you will be able to, and I'll write these in first person, I will be able to, ... solve quadratic equations where the value of x has an imaginary component. And two, that you will be able to connect the number of x-intercepts to the number of real solutions for an equation. Period. Okay. So let's just jump right in and get started. We have 5-124. Consider the equation x squared equals 2. How many solutions should we get? Well, we know that when we're taking the square root of a positive number, in order to solve a quadratic, that will give us 2 solutions. We should get 2. That's because there are 2 such x values, which when squared would give you positive 2. And we know that there is a connection between the number of solutions, number of real solutions for a quadratic equation, and the number of x-intercepts its related graph should have. There should be 2. The number of x-intercepts is the same as the number of real solutions. Well, let's go ahead and solve the equation now. I have x squared equals 2. I'm going to write the answer in both exact and approximate forms. I take the square root of both sides to solve this, and I get x equals plus or minus the square root of 2. There. That's the exact versions. I have x equals positive root 2 or negative root 2. If you want, you can leave your answer just as plus or minus square root of 2. That has the same amount of information. Now for the approximate version. This is exact. And now we need to write the approximate answers. So I take 2 and I square root it, and I get about 1.41. So x is approximately equal to positive 1.41 and negative 1.41. I call that approximate because I had to round. This is a decimal that does not end. Okay, that's a quick review. Moving on. 5-125. Mathematicians throughout history have resisted the idea that some equations may not be solvable. Still, it makes sense that x squared plus 1 equals 0 cannot be solved because its related graph, f of x equals x plus 1 squared, has no x-intercepts. The graph of f of x equals x squared plus 1 looks like this. Its vertex is at 0, 1, and it has no x-intercepts. What happens when we try to solve this? Well, let's go ahead and do that. X squared plus 1 equals 0. I subtract 1 from both sides. I get x squared equals -1, meaning that if I take the square root of both sides, I get x squared equals plus or minus the square root of -1. But let's just try to put that in our calculator. What happens? The square root of -1. That's an error. So go to the error. -1 does not have a real square root. So up until now, there's no solution to this. So there are no real solutions. Which agrees with our graph. No real solutions, no x-intercepts. No real solutions, no real solutions, no x-intercepts. But finally, today's the day. We're taking the story further. Next page. Imagine it's the 1500s. We're in Italy. This mathematician, Raphael Bombelli, invented the imaginary number. Invented is kind of a funny word because truly it was a discovery. But anyway, it's called I, and it's defined to be the square root of -1. And I squared is equal to -1. Now that we have this, it becomes possible to solve x squared plus 1 equals 0. Those solutions are plus and minus the square root of -1, which give x equals I and -I. It's kind of amazing. We can even simplify the negative square root of 16. We rewrite it as this. We're going to use this definition to rewrite I in each of the following. And I'm just going to put the definition here in a way that I find is more clear. So I, by definition, is the square root of -1. I squared, by definition, is -1. Okay. This is the square root of -4. I can rewrite this as the square root of -1 times 4, which is the square root of -1 times the square root of 4. And that's, would you believe it, I times the square root of 4. Wow. Now the square root of 4 is 2. So I would get this in a final format of I times 2. And usually in math, just by convention, we write letters after numbers. So It's more polite to write 2i, although I times 2 has the same value. All right, let's look at this one. This is 2i times 3i. Well, when we multiply numbers, it doesn't matter what order we multiply them in. So I'm going to do this as 2 times 3 times I squared. I times I is I squared. That's 6. Now I squared is -1 times -1. That's one of our definitions. So this is just equal to -6. Next problem. This is -5 times 2i squared. Well, notice what part the parentheses are insulating with the square. Just the 2 and the I. Sometimes I see students squaring that -5, which would not be correct because it's not inside the parentheses. Okay, so I have -5 times 2 squared times I squared. That's -5 times 4 times I squared is -1. -1. That's +20. Last part in this row, this is the square root of -25. I rewrite that as the square root of -1 times 25, which is the square root of -1 times the square root of 25, which is I times 5. The square root of -1 is I. The square root of 25 is 5. And I rewrite that as 5i because I like it more when the numbers are before the letters. Either would be correct. This is more polite. It's a manners thing. It's about fitting in. You don't have to fit in. You can write it as I times 5. 5i is how you'll always see it written in books. So you should know how to read that. Okay. Next problem. We consider the graph of the function f of x equals x squared minus 4x plus 5. This is that graph. Does the graph cross the x-axis? Well, I'm looking at it and it doesn't, so no. Does the equation have real solutions? Okay. Well, this is not written in perfect square form, but I know that the number of real solutions is the same as the number of x-intercepts. So I know that it does not, because the number of real solutions is the same as the number of x-intercepts. So no x-intercepts means no real solutions, period. All right, let's experience this in terms of algebraic solutions. So I'm going to complete the square. The first step of completing a square is to remove the constant term by subtracting it from both sides in this case. So I have x squared minus 4x equals -5. Now I'm going to complete this square. I take my x squared term, I put it right there. I break my -4x into even pieces. I had 4 of them. Is this a rectangle? Yeah, it is. This is also a rectangle, but it's a perfect square rectangle. Aha, almost. I need to fill in the middle. Anyway, I have -2x on one side and -2x on the other side. Finding the outside, that tells me that this little piece right here had better be +4. Because -2 times -2 is +4. All right, so I've got 4 here. if I'm adding 4 to this side, I'd better add 4 to the right-hand side as well. So that gets me x minus 2 squared equals -5 plus 4 is -1. Now I'm trying to solve, and I claim, now that we know about imaginary numbers, we can. So I'm going to take the square root of both sides. This is now x minus 2 equals plus or minus I. Solving that with two equations is giving me x minus 2 equals positive I, or x minus 2 equals negative I. Can you see? There. I add 2 to both sides. And my final result is x equals 2 plus I and x equals 2 minus I. They're not like terms, they cannot be combined. So you end up with it written in these two parts. You may notice that I wrote the 2 in front of the letter, even when I'm separated with, well, actually, this is not the same as it would be normally. If I were a variable, and it's not, it's a number, but if I were a variable, then I would have written it first. But for imaginary numbers, I always write the imaginary part after the real part. 2 is a real number, I is imaginary. Okay, next question. Next part of this question is part D. Hope you can see. Okay, part D. Let me focus. Did that work? Can you see? Focus. Aha. Okay, well, I think it's as good as it's going to get. Use our new understanding of imaginary numbers to rewrite the solution in part B using I, and not with the square root of a negative number. Oh, we did it ahead of time. We have x equals 2 plus I and 2 minus I. Done. Next page. This is the last page. Yay. Moving right along. Okay. This is 5-128. In problem 5-127, we found the solutions to a quadratic equation, x squared minus 4x plus 5. Ding, 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 ding. We have new vocabulary. The roots of a polynomial function f of x are the values x such that f of x equals 0. We have seen that the solutions to equations can be real or complex. Complex. This is any number with a real and imaginary component. Period. Any number with a real and imaginary component is considered complex. Okay, so we have solutions to equations that can be real or complex. So it follows that roots, that's the main word that we're doing, can also be real or complex. Compare and contrast what happens with the graphs and equations for the 3 parts A through roots. This should say roots. For the 3 roots in parts A through C below. Okay, so part A. We're going to use our graphing calculator. In other words, I'm going to draw a graph on this piece of paper. And then we're going to use that graph to determine the roots of f of x. Maybe we should use a graphing calculator. No, that's okay. Y equals x plus 3 squared minus 4 graph. Okay, it's pretty clear. It goes right through. So I'll draw that graph really quickly. This is at 1, 2, 3, 4, 5, -5, 0, and this is at -1, 0. And my roots are the values of x such that f of x equals 0. Now when I'm on my x-axis, f of x is 0. So f of x equals 0 when x is -5. And f of x equals 0 when x is -1. My answers are -5 and -1. You might say, why do we need another name for x-intercepts? Well, if you were to say that, I would respond. Roots are an umbrella term These are roots. And in the umbrella are x-intercepts, but we can also have, those are real roots. But we can also have imaginary roots. And we don't want to discount them. So x-intercepts are special roots. They're real roots. They're roots that show up on a two-dimensional graph. Okay, next, part A. Use our calculator to graph f of x equals x plus 3 squared. Use the graph to determine the roots of f of x. All right, here we go. Y equals x plus 3 squared. Graph it. There it is. Oh my gosh, it only has one root. Check out that smooth curve. Oh, so good. Anyway, the roots are x equals -3. When f of x equals 0, x equals -3. Next, we're going to use our calculator to graph this one. We're going to use the graph to determine the roots. Okay, y equals x plus 3 squared plus 4 graph. Okay. How am I supposed to do this? Part C doesn't have an answer. Oh, look, these are mislabeled. This should be part B, part C. You know what? I can't. I can't use a graph to determine the roots because there are no x-intercepts. Therefore, the roots do not show on my graph. Period. Did you know that 3 dots means therefore? Isn't that pretty? Okay, part D. I guess I'd better use an equation because graph's not doing it for me. All right, I have h of x equals x plus 3 squared plus 4. And I'm going to solve this by setting h of x to 0. I want roots. So I set the function to 0, just like I would if I were finding x-intercepts. So I have 0 equals x plus 3 squared plus 4. I subtract 4 from both sides because I want to be able to take the square root, and I have -4 equals x plus 3 squared. I continue. -4 equals x plus 3 squared. I take the square root of both sides. That gets me the square root of -4 is the same as 2i. I'll show you why on the side. I have the positive 2i equals x plus 3, and I have the negative 2i equals x plus 3. I subtract 3 from both sides of this version of the equation, and I get x equals -3 plus 2i. I subtract 3 from this side of this version of the equation, both sides, and I get x equals -3 minus 2i. And that's the best I can do because they're not like terms. And then, as promised, -4 equals 2i because the square root of -4 is 2i because that becomes -1 times 4, which is I times the square, which becomes I times the square root of 4. The square root of 4 is 2, so I have 2i. Okay, describe in words the relationship between the graphs of parabolas and the kinds of roots their equations will have. Okay, so when we crossed the x-axis, then the equation had real roots. So if our graph has x-intercepts, then our equation has real roots, as in real numbers, nice and comfortable. If our graph does not have x-intercepts, then our equation has imaginary roots. This consequence is sometimes referred to as the fundamental theorem of algebra. Well, this is half of that theorem. You'll learn that next year. Okay. So if we have x-intercepts, we have real roots. If we do not have x-intercepts, then we have imaginary roots. That's an important consequence of this lesson. Next problem. Last problem. Wow, yay! We're doing so good. Okay. The sum of a real number and an imaginary number, such as 2 plus 3i, is called a complex number. Vocabulary. A complex number can be written in the form a plus bi, where a and b are both real. We use the definition of I and our understanding of real numbers to write each of the following expressions. And let's just keep our definition handy, and then we'll also have this. Okay, so I distribute the 2. This becomes 6 plus 2i. And this is a final answer. All I'm doing is I'm writing this as a complex number where both the 6 is real and the 2 is real and the I is imaginary. This is the format that all complex numbers take on. Okay, next. 10 minus 9i minus I. Well, I have like terms, so I have 10 minus 10i, and that's it. Real part, imaginary. Next. -2 minus 7i plus -1 plus 4i. These parentheses are really doing anything for us. But I know from working with many of you that it would help you to understand how come I can just drop the parentheses. And it has to do with the fact that there is really a hidden one right here. This, if I were to distribute this one, it would become -2 minus 7i. And this would become -1 plus 4i. Because nothing really changed, I could have just ignored the parentheses. But I'm not really ignoring them. I'm just understanding the fact that it's the same as distributing one in. Anyway, let's combine like terms. My real components are here. That's -2 minus 1, which becomes -3. My imaginary components are here and here. That's -7i plus 4i, which becomes -3i. Final answer. Moving right along. Here we have -8 plus 2i minus 1 minus 6i. This is not exactly the same as the one before because here I was adding the two complex numbers and now I'm subtracting one complex number from the other. So this becomes -8 plus 2i, and I have to distribute that minus. So -1 plus 6i. Okay, combine like terms. -8 minus 1 is -9. (2i) plus 6i becomes +8i. Final answer. And now for the fun one. Multiplication. I'm going to use an area model. I have 1 minus I. I have 8 minus 6i. I should make that zoom in. 1 times 8 is 8. 8 times -i is -8i. 1 times -6i is -6i. And here I have +6i squared. What does that turn into? Well, I have 8 minus 8i minus 6i plus 6i squared. That's 8 minus 14i plus 6i squared. But, I squared is -1. So this becomes 8 minus 14i plus 6 times -1, which is 8 minus 14i minus 6. Final answer, 2, because 8 minus 6 is 2, minus 14i. Okay, let's go over the most important things we did. Most important thing, definition of I. I is the square root of -1. I squared equals -1. A complex number is written as a plus bi, where I is imaginary and a and b are both real, meaning a and b are numbers that we're used to. When performing operations on imaginary numbers, everything follows as a consequence from the definition. You do everything you would do if you were combining like terms and I were a variable, except that sometimes you need to simplify it based on the fact that I is the square root of -1 and I squared is -1. Graphing. If your graph has x-intercepts, then your equation has real roots. If your graph does not have x-intercepts, then your equation has imaginary roots. some practice with performing operations on imaginary numbers. Yeah, that's it. Imaginary numbers have a lot of applications in physics and other sciences, especially when it comes to electricity. They're not imaginary, they're just poorly named. I hope you all have a wonderful day, and I'll see you for the next lesson. Bye.